a few distinct kinds of hybridizations: sp, sp2, sp3, dsp3 and d2sp3, and a bond acts as one of these effective pair of electrons where it is a single, double or a triple bond. The number of electron pairs of the central atom will determine the arrangement. If there are, say, 3 such electron pairs, it's a trigonal planar structure, as in the case of one of the carbon atoms in ethylene. If it has got 2 electron pairs on the central atom, it will be an sp hybridized orbitals with 2 pi bonds, like as in acetylene or in carbon dioxide, and so on. Let us take up a simple exercise. Say I ask somebody to draw the Lewis structure of phosphorus pentachloride and to predict the shape of the phosphorus pentachloride molecule. So it will be trigonal bipyramidal and there will be 2 distinct kinds of bond angles. The bond angle in between this chlorine, phosphorus, chlorine, this angle will be 120 degrees, while if you look at the axial bonds, that will be the bonds which will be, actually perpendicular to the molecular plane, will be 90 degrees. This is how it is done. Combination of 1d, 1s and 3p orbitals gives a trigonal bipyramidal arrangement of 5 equivalent hybrids. And this is the structure. So this angle, this Cl, phosphorus, Cl, this angle is 120 degrees, and this chlorine, this phosphorus and this chlorine, if you look at this angle, this entire angle is actually 180 degree. So from the molecular plane, with respect to this molecular plane, this angle Cl, P, Cl, this angle is 90 degrees. Go to the next exercise, Say somebody asks me to draw the Lewis structure of xenon tetrafluoride and predict its shape. So in case of xenon tetrafluoride, this is the Lewis structure, and if you go over to the hybridization, it can either be sp3d2 or d2sp3. Now, this gives you an octahedral arrangement like this. So there will be 6 electron pairs, so that will necessitate an octahedral arrangement. So all of these angles will be 90 degrees because this xenon, this fluorine, xenon, fluorine angle, this is also 90 degree, and this fluorine, xenon, fluorine angle is also 90 degree, where this is not in case of xenon tetrafluoride. It is not a xenon over here, it is a lone pair. So all the angles, all these 4 angles are essentially the angles on this particular plane. So keep in mind, the axial positions in the case of xenon tetrafluoride is taken up by 2 lone pairs, one above the actual plane of the molecule, the other below the actual plane of the molecule, like this. Okay, so let us make a concept check. So first of all, we draw the Lewis structure, say for HCN. Then we use the idea of which hybridized orbital to use, and then we go over to find out which are the sigma bonds and which are the pi bonds and show them there. Okay. So, as certain cases, you can take up these individual molecules and practice the kind of bonding they can do and the corresponding molecular shapes. Okay, so using this model, the steps are: first draw the Lewis structures, then determine the arrangement of the electron pairs using the VSEPR model, followed by specification of the hybrid orbitals needed to accommodate these electron pairs, and let us take up one of such examples. First, the example says, describe the bonding in water molecule using the localized electron model. So, how to go about it? Fine. So, this is the molecule. These are the lone pairs. So, since there are 4 electron pairs, 2 of which are bond pairs, these 2, and the molecule will be V-shaped. This is very simple. So, there are how many such possibilities? So, what we can observe is bonds that are formed from end-to-end overlaps of orbitals along the axis of the orbital are called the sigma bonds. The bonds that are formed by the sidewise overlaps in between the unhybridized p orbitals are the pi bonds. All single bonds are sigma bonds necessarily. This is the sigma framework of the molecule, A double bond consists of always a sigma bond which generates the basic molecular frame and one pi bond. A triple bond is always made up of again of one sigma bond which is a part of the molecular frame and two pi bonds. So there can be many examples which you can go through. So this is a relatively complex molecular system. It's an insecticide that is obtained commercially. It's called Sevine. The structure of this molecule is like this. If you count, there are 27 sigma bonds and 6 pi bonds in total. Some practice problem. So this is difluoroiodine or iodine difluoride. So this is iodine difluoride plus. So this is a Lewis structure, the Lewis electron dot structure. This is sp3 hybridized. So the VSEPR theory will actually predict it to be tetrahedral on the basis of the hybridization model, and it will be a bend-shaped molecule with a bond angle of 109 degrees 5 minutes. Now the molecular shape of another molecule, these are all examples. This is SOF4. This has 5 electron pairs. The VSEPR theory will predict it to be trigonal bipyramid. The sulfur is in the sp3 dehybridized state, and if you just move ahead, this is the structure. In the acetylene molecule, which I have already discussed, this is a clear-cut case of sp hybridization, and the VSEPR theory will predict it to be linear in structure like this. Now let us move on to another very important model, which is the molecular orbital model. This is one of the models where the localized electron model, as we have just seen, it predicts and justifies molecular shapes in a fantastic manner. But it neglects certain things. It neglects the bond energies. The molecular orbital theory is a more quantitative form, is a better form of bonding, or is a better theory or model for bonding, because it clearly gives us an idea of the corresponding energetics associated with these bonds. Molecular orbital theory also predicts the idea of resonance. Molecular orbital theory essentially thinks a molecule to be a collection of nuclei and electrons, and these electrons are assumed to be occupying orbitals as much, very similar to their occupancy in atoms, but having the orbitals. These orbitals are such that these orbitals, the molecular orbitals, span the entire molecule, not just over the atoms. So the electrons are assumed to be delocalized, and these electrons are assumed to be spread, to be present in between the atoms that forms this molecule, in between the atoms that really constitute this molecule. So there is the chance of the probability of electron probability of our MO. So the electron probability of both molecular orbitals is centered along the line passing through the two nuclei. These molecular orbitals are the sigma molecular orbitals, very much similar to the concept of a sigma bond in the hybridization picture. In the molecule, only the molecular orbitals are available for occupation by the electrons, so there is no trace of any sort of atomic orbitals within the molecules. So what are the key ideas of this model? So the key ideas of this model are: all valence electrons in a molecule exist, they remain in the molecular orbitals with given energy, and each molecular orbital has a characteristic energy. The valence orbitals of each atom, they are not independent of one another, but they interact as a whole to form a set of molecular orbitals. These interaction results in what we call as a linear combination of atomic orbitals to form the molecular orbitals. Keep in mind the fact that this interaction is very much similar to the formation of hybrid orbitals, but here it is more quantitative in the sense that the energetics is involved in the process. Each pair of atomic orbitals interact to form a set of bonding and a set of anti-bonding molecular orbitals. We will discuss about bonding and anti-bonding molecular orbitals. The energy for bonding molecular orbitals is lower than the corresponding sum of energies of the atomic orbitals, and the energies associated with the antibonding molecular orbitals are higher as compared to the sum of the energies associated with the corresponding atomic orbitals. So let us take up the simplest case, the hydrogen molecule. What might have happened? One thing that can happen is, say we label the two hydrogen atoms to be A and B. So this is the 1s orbital of the A hydrogen atom and this is the 1s orbital of the B hydrogen atom. They can combine in two ways. One possibility of combination is that they can be added in phase to form a bonding molecular orbital. This we call as the molecular orbital 1 or MO1. Similarly, they can be subtracted. That means they combine out of phase and they will be having a zone over here. As the pointer is showing over here, they are having a zone where there is no electron density in between. This is the antibonding molecular orbital, which we call as the MO2. So what about the energetics? As I have just said that this has a definite energetic structure. So this is the diagram for the hydrogen molecule. The first thing is, see, this y-axis, the axis over here, the vertical axis, gives you an idea of the relative energies of the bonding, that means MO1 and MO2, the antibonding molecular orbitals. These are the energies associated with the two atomic orbitals, and see, this bonding molecular orbital has an energy lower to the corresponding energy associated with the atomic orbitals, whereas the antibonding molecular orbital has an energy which is higher than the energies associated with the corresponding energies of the atomic orbitals. Now, these are the electron probability distributions. So, in the case of the bonding orbital, so in between the two nuclei of these two hydrogen atoms sitting over here, these two black dots, you can have an electron density. So, this means that there is a bonding zone, there is a bonding region that has formed in between. So, this particular orbital, MO1, which we call as the bonding molecular orbital, this has got a particular structure where in between the two nuclei there is a definite amount of electron density, which is a representation of the bonding nature of these orbitals. Okay. So, as I have just said, MO1 is lower in energy than the energies associated with the s orbitals, 1s orbitals of the free atoms, and MO2 is higher in energy. Bonding molecular orbital, it's the lower energy orbital. Antibonding molecular orbital is the higher energy orbital. So, this is a clearer view of the corresponding MO diagram. So, how to fill up these electrons in these MOs? It is very simple. So, once you have drawn the molecular orbitals, the bonding and the antibonding ones, then just like the filling up of the atomic orbitals, you put each molecular orbital, or you try to occupy each molecular orbital by means of two electrons with opposite signs. So, if one electron is plus half in its ms value, the other will be minus half. So, one is alpha spin, the other is a beta spin. So, and the total number of orbitals are always conserved. The total number of orbitals, the total number of atomic orbitals will always be equal to the total number of molecular orbitals that are eventually formed as a consequence of this bonding. What is a bond order? We define a quantity called a bond order by means of this. The bond order is actually defined by the total number of bonding electrons minus the total number of antibonding electrons divided by 2. The larger the bond order, this is equivalent to saying that the greater is the bond strength. So, any molecule having a larger bond order will be a stabler molecule as compared to the one which has a lower bond order. So, bond order is a measure of net bonding interactions. In case of a stable molecule, which has a definite stability, the bond order must be greater than 0. A 0 bond order will mean that no bond has formed and that means no molecule formation has taken place. The higher the bond order, the stronger is the bond. So let us take up an example, the simplest one, the hydrogen. So if I draw the molecular orbitals, then fill them up, the molecular orbitals. So prior to the formation of the molecular orbitals, in case of the two nascent hydrogen atoms, each of the 1s orbitals used to have 1 electron each. Now, once these bonds were formed, these two electrons must occupy the lower energy orbital, that means the bonding orbital. Now, if I go by the definition of bond order, then the number of electrons in the bonding orbitals, which is 2, minus the number of electrons in the antibonding orbitals, there is no electron in the antibonding orbital at all, so it's 0 divided by 2. This means it has a bond order of 1. A bond order of 1 will be a rough indicator of the number of bonds in between the two atoms. It is a single bond, and since it is greater than 0, hydrogen molecule is a stable molecule. Now, energy level for the first period of elements, you can have certain rules. So, to fill the molecular orbitals for atoms containing 1s valence electrons, hydrogen and helium, so you have to first determine the number of electrons in the molecule. You have to fill in the energy level diagram from the lowest to the highest, and fill each orbital with a pair of electrons with opposite spins, and keep in mind the Pauli exclusion principle in the same manner as you have done in the case of the atoms. So, this is the filling up process, like this. So, if you keep on filling up like this, this is the case for the helium-2 molecule. Now, this is a curious example. See, helium in its atomic state has got the 1s2 electronic configuration. So, this is the atomic helium-1, this is the second atomic helium. So, once the molecular orbital forms, there are two molecular orbitals. One is the bonding, the other is the antibonding. So, once these are formed, you see that there will be 2 electrons in the bonding and 2 electrons in the antibonding orbital. So, what will be the bond order? In case of this helium, the bond order will be 2 minus 2 divided by 2 equal to 0. So, helium-2 molecule shouldn't be formed. So, let us go over to a different example, H2 minus ion. So, this was H2, you have to put an additional electron into the molecule. So, you put the additional electron in the antibonding orbital. Once this additional electron is put over here, then the bond order changes to half from 1 in case of the neutral hydrogen molecule. Okay, let us take up a certain simple exercise on the molecular orbitals. It has been said to use the MO theory to describe the bonding and stability of two molecules, H2 and H2+. The first thing is that the first system has got 4 electrons, and this is the molecular orbital diagram. The bond order is 0, so it won't be formed. In case of H2+, if you just move ahead, it has got 1 electron. It will be residing in the bonding molecular orbital, so it will be having a bond order of half, so it will be formed.